Bismillahirrahmanirrahim. Another model that is considered in this chapter is Russell measure models. We now introduce a model due to Russell, described as the Russell measure model by Fair and Lowell. Their formulation is difficult to compute. We therefore turn to a more recent development due to Pastor, Ritz, and Servan. This model is, as you see, the objective function is minimization with the linear fraction function that is summation of theta I over m, and the denominator is summation of phi r from 1 to s over s. The constraints, as you see here, of course, for the constant return to scale assumption, note that we don't want to increase any input, so theta I is less than or equal to 1, and of course bigger than or equal to 0. And since we don't want to decrease any output, we should have also phi r bigger than or equal to 1. Pastor et al. Refer to this as the enhanced Russell graph measure of efficiency, but we shall refer to it as ERM, enhanced Russell measure. Theorem 4.14 says ERM as formulated before and SPM as formulated in 4.48 are equivalent, means the lambda j star values that are optimal for one are also optimal for the other. Of course, their objective function also as the efficiency value are the same. So we have ERM model as you see here. Note that we, for the simplicity, we assume that all the data are strictly positive, and we want to prove that ERM is equivalent to SPM. For proof, let lambda star, theta star, phi star be an optimal solution for ERM. Then the main constraints are in equality for the optimal solution, main constraints of this model. Indeed, we proved that in the optimality, all these constraints must be in equality. So the model, in the model, we can put equality instead of inequality in these constraints. To prove, first we consider the first set of the constraints. So for any arbitrary optimal solution for ERM, we prove first that these all should be in equality. Uh, the proof is by contradiction. If there exists H, indeed, if there exists a constraint that is not equality, this means is in strict inequality, then there should be exist a positive epsilon. Indeed, epsilon is between 0 and this value, such that we have this inequality. However, note that if we put epsilon the bigger value, of course this epsilon can be also the upper bound, so this can be equality, not necessarily in strict equality. If we put epsilon the upper one, this is equality, and for the other epsilons this is strictly inequality. However, we always have this for I equal to h. For the others, the other I, we have equality. For this h, we have inequality or equality. If we change the solution as this, and since the other constraints are the same for this solution, we indeed have a feasible solution like this, lambda the same, but theta, only theta h star is changed to theta star h minus epsilon, and the other are the same. Note that here EH means a vector with the h component equal to 1 and the others equal to 0. It's obvious that this is feasible for ERM. However, note that the optimal objective function was this value, and obviously this is bigger than this. That is the objective function corresponding to this feasible solution. And this is contradiction because the model was minimization, and the minimum feasible value cannot be bigger than a feasible objective value. This contradiction shows that we cannot have any h with strict inequality, so we should have all these constraints in equality for the for any optimal solution. Similarly, we have all the constraints for the outputs also in equality u say y. Hence, now that we know in the optimal solution we have these inequalities in equality, all are binding, so we can change these to equality, and this model is equivalent. That means ERM is equivalent to a model that we change the inequality to equality in the main constraints. So we have ERM is equivalent to this. Now, by adding XIO to both sides of the first set of the constraints and YRO to both sides of the second sets of constraints, uh, it is seen that this model is indeed can be right as this one, and these are equivalent, these are the same indeed. Now by putting si minus equal to 1 minus theta I by xio, this is 1 to 1, so we have theta I is 1 minus si minus over xio, and sr plus equal to this vr minus 1 there by yro, or this vr is equal to 1 plus sr plus over yro. By putting this, now we want to write the model in new variables. We consider all the constraints. The first set become this summation plus si minus equal to xio. The second one, this minus sr plus equal to this. Lambda j is equal greater than or equal to 0 are the same. However, here we have theta and phi r, but in the new model we want to remove these variables. Note that theta I bigger than or equal to 0 means from this that si minus is less than or equal to xio, and theta I less than or equal to 1 is equivalent to si minus bigger than or equal to 0 from this, and phi r is bigger than or equal to 1 if and only if sr plus is bigger than or equal to 0. So by considering this and putting the new variable, indeed theta I phi r, we put their equivalent value in the objective function, and we have one that was equal to ERM is also equivalent to this model. We change the variable, put instead of theta I it's equivalent and phi r is equivalent value in the objective function, so we have the objective function is minimizing 1 where m by summation of 1 minus si plus over xi. This is summation of 1 m times, so it is m by 1 over m, it is equal to 1, and the other one is 1 over m by summation of si minus by over xio, of course with minus sign, negative sign here, so the numerator become this, and similarly the denominator is equivalent to this. As you see, this is the objective function of the SPM model. For the constraints, we only put their equivalent value si minus sr plus from this in these two sets, and from this part, instead of these constraints, we have these and these constraints relatively. However, note that from the first set of constraints, we always have si minus is equal to xio minus this value, and since the x data are positive and lambda j is a non-negative, this is obviously less than or equal to xio. So si minus less than or xio is redundant and can be removed from the model. And if we remove these constraints, si minus less than or equal to xio, you can see that this is indeed the SPM model. So we proved that ERM is equivalent to the SPM model.